Imagine being on a bridge so long you could drive over it for hours and still not see the end. Behold, the world's longest bridge, the Danyang-Kunshan Grand Bridge. This jaw-dropping megastructure that cost a whopping $8.5 billion spans over 102.4 miles, and 5 cities across China is so long that the amount of steel used to build it can build 60 Eiffel Towers. Riding over it feels like being on a never-ending road suspended 100 feet in the air. This marvel of engineering was meticulously built to not only defy earthquakes, but also remain unshakable in the face of the strongest typhoons and can even take a hit from a 300,000-ton ship without breaking a sweat. The construction of the Danyang-Kunshan Grand Bridge was no easy feat. Building over places like the soft soil of the Yangtze River Delta and having to construct 2,000 pillars in the middle of a lake, engineers had to get creative. It took 4 intense years to build, with a workforce of 10,000 people. But China has officially opened the world's longest bridge. What is the Danyang-Kunshan Grand Bridge? How will it fix China's traffic problem? And most importantly, how was it built? Before the Danyang-Kunshan Grand Bridge existed, travel in the eastern coastal area of China, especially between major cities like Shanghai and Nanjing, was a real headache. It was so bad that it took 4.5 hours to get between Ningbo and Jiaxing, and the only thing that could solve it was a railway. But you see, the region's geography, with its lowland rice paddies and extensive network of rivers, lakes, and canals, made it a tough terrain to build on. The soil is so soft and silt-heavy, which isn't great for building stable structures, especially something as heavy as a railway. So imagine trying to lay a railway line directly on this soft, marshy ground. Any structure built on it would risk sinking or shifting. Not something you want for a high-speed train zipping across the country. And it isn't just about the soil either. In the area where the Danyang-Kunshan Grand Bridge is located, there is a dense network of rivers and lakes with over 150 river channels wider than 20 meters. The region is so crisscrossed with water bodies that constructing a normal railway would mean constantly building small bridges and causeways, which is expensive and time-consuming. Then there's the issue of the fertile farmland and the communities living there. Building a ground-level railway would mean bulldozing through these areas, displacing people and disrupting lives and livelihoods. China had to think of a solution to build a fast, stable railway without turning the whole area upside down. That's where the Danyang-Kunshan Grand Bridge comes in. Going for an elevated bridge, this giant viaduct, they built a stable, high-quality railway line that doesn't mess with the delicate soil or disrupt local communities and farmlands. Situated in the Jiangsu province, the bridge connects the 2 major urban hubs, Shanghai and Nanjing, along the high-speed Beijing-Shanghai railway line, making the 1,000-kilometer Beijing to Shanghai journey possible in under 5 hours, and that 4.5-hour journey between Ningbo and Jiaxing only about 2 hours. A game changer for people's daily commutes, business travel, and the overall connectivity of the region. The bridge's main purpose in the area was to solve the railway traffic. It was built by the China Road and Bridge Corporation, a subsidiary of the China Communications Construction Company and a major player in China's civil engineering sector. The construction of the Danyang-Kunshan Grand Bridge commenced on April 18, 2006, and culminated with its opening in June 2011. As stated earlier, it demanded an investment of about $8.5 billion, costing roughly $51 million per mile. It's a viaduct bridge comprising several small, interconnected sections designed to overcome the unique challenges of the Yangtze River Delta's varied terrain, which we'll get into in a bit. Structurally, the bridge showcases an impressive use of over 4,000 pre-stressed concrete beams. These beams, each reinforced with high-tensile steel wires, were engineered to withstand immense loads, ensuring the bridge's integrity under the weight of high-speed trains. The pre-stressing process involving the tensioning of steel wires before pouring the concrete was crucial in providing the required compressive forces to counter potential tensile stresses. In addressing the seismic risks in the region, the bridge incorporated advanced earthquake resistance engineering. It features base isolators, elastomeric bearings, and sliding plates in its foundation, allowing controlled lateral movements during seismic events, thereby dissipating the seismic energy. This is complemented by reinforced concrete columns and shear walls in the piers, capable of withstanding significant lateral forces. Expansion joints are integrated into the rail tracks to accommodate ground movement during tremors, thereby averting rail buckling. The bridge's ability to withstand typhoons is another engineering highlight. Beyond selecting corrosion-resistant materials, the design included aerodynamic considerations with streamlined bridge elements and wind tunnel testing to gauge the impact of typhoon-generated forces. Its anchorage systems were engineered to withstand the dynamic loads of strong winds, and stainless steel reinforcement and protective coatings were used to enhance corrosion resistance. The construction process itself was marked by innovation, particularly in overcoming terrain and urban challenges. A mix of cable-stayed and beam bridge designs was employed to span the varying widths of rivers and canals. Prefabricated segments for the bridge's elevated sections minimized disruption and expedited construction in urban areas. The section spanning the open waters of Yangcheng Lake in Suzhou, supported by 2,000 pillars, is particularly notable. This part required meticulous planning and execution to protect the lake's ecosystem. The bridge's long-term maintenance plan is equally rigorous, utilizing advanced, non-destructive testing techniques for regular inspections and a proactive approach to corrosion protection. This includes applying protective coatings, implementing cathodic protection systems, and periodically replacing corroded components. Designed to withstand extreme weather conditions and direct hits from naval vessels weighing up to 300,000 tons. The Langfang Qingshan Viaduct, a significant bridge segment, extends for 70.8 miles, 114 kilometers, making it the world's second longest bridge. With the construction of this bridge came massive controversy surrounding the curvature of the Earth, particularly between those who believe the Earth is flat and those who adhere to the scientific fact that it is round. Those who understand Earth as a sphere recognize that large-scale engineering projects like this bridge must account for Earth's curvature in their design. The engineering of the Danyang-Kunshan Grand Bridge indeed considered the Earth's curvature. Over long distances, the curvature becomes a factor in construction and surveying. Engineers used advanced surveying techniques, accounting for the Earth's curvature, to ensure the bridge's alignment and structural integrity. This process involves precise geodetic measurements incorporating the Earth's radius to calculate the curve and ensure that each bridge segment aligns correctly with the next. The bridge involved segmental construction techniques, where small segments were built and assembled. The precise alignment of these segments took into account the Earth's curvature. This approach allowed the engineers to construct the bridge in a manner that follows the Earth's surface accurately over its entire length. To avoid impacting the lake's ecosystem, these temporary enclosures in water allowed construction workers to operate on the lake bed rather than the surface. This method simplified operations and protected the lake's water quality. Any sewage or construction waste generated was carefully managed, treated on shore, and disposed of in a way that preserved the ecological balance. As previously stated, the bridge's design also addresses the challenges posed by the varied and complex environments it spans. One significant engineering challenge was to manage uneven settlement, a common issue in areas with varied environmental conditions. This was overcome using a combination of pier caps and friction piles in the bridge's foundation. The friction piles, driven deep into the soil, provided load-bearing support, while the pier caps distributed the pressure evenly, ensuring the bridge's stability and longevity. The Danyang-Kunshan Grand Bridge serves as more than just a transportation link. It plays a pivotal role in the economic development of the southern Jiangsu region, a vibrant economic area in China. This region, encompassing cities like Suzhou, Wuxi, and Changzhou, may only account for 0.3% of China's total land area and 1.7% of its population. Still, it punches above its weight in economic terms, contributing a significant 17% to China's total import and export volume. All in all, this bridge is nothing short of impressive. Thank you for watching, and please do like, share, and subscribe. Do you live in or have gone to China? Share your thoughts about it and how it's impacting lives in the comments section. Don't forget to hit the bell icon. See you in the next video.